Okay, welcome all, and today is a very exciting lecture where we'll see maths meets chemistry, and we'll see the application of mathematical basis on the chemical structure of a substance or a compound. So we'll deal with a few of the many situations. Of course, chemistry itself makes our life. So our life itself is chemistry, or chemistry is life. Okay, so this entire lecture is dedicated for the love of chemistry. The first operation which we often encounter in mathematics is the sigma operation. And what is sigma? Is nothing but the summation. So you can just look as if we have a box which contains sigma, which means like you have infinite summations available in picture. So sigma xi, when I is running from 1 to n, it simply means you put I equals 1, so you have x1, put I equals 2, you have x2, put I equals 3, you have x3. So it's a box containing xi, and every time I changing, those elements are getting added. So this is just a cool notation of writing this summation x1 till xn. X can be anything, x can be number of objects in a basket, x can be molecules or whatever. So xi's are the number that are being summed. It could be expression involving I is the summation index. So basically it's an indicator of something changing. I1 tells that you have to start sum from I equals 1. N tells where to stop, right? So it's a stopping summation when we have to reach at I equals n. Let's take a numerical example. Let's say 1 plus 2 plus 3 plus 4 plus 5. So you can write this in a very cool notation as sigma I equals 1 to 5i. It means this is something which can take different values. So if I'll keep I1, it's 1. If I'll keep I2, it's 2. If I'll keep I3, it's I becomes 3. I4, I5. Now this sigma notation means each and every objects when you are keeping I, just it needs to be added, and that will give you 9, 12, 14 and 15 is the answer. Let's take one of the basic example. What's the value of I equals 4 to 7 I square. So now again we have a box containing I square, and sigma just hit this. Every time you put I values, it will create a new numbers, and sigma means we need to add them. So I equals 4 will give 4 square. That's written over here. I equals 5 is 5 square. I equals 6 square. I equals 7 square. And if you add, it's 126. Okay, so as you can see, this summation index might not be of numbers. For example, finding relative molecular mass of a molecule, we can even sum all of its constituent element. Let's take a simple example. Let's say if I have to find the relative molecular mass of CH4. So what do we have to do? So we have one carbon atom, and the mass of one single carbon atom is 12 gram. Like I mean 1 mole of that, right? Plus we have 4 hydrogen atom, and the mass of each hydrogen atom is 1 gram, or say basically 1 AMU. So a mole of hydrogen will give 1 gram. So if you calculate, so 1 mole of CH4 is gonna give you 16 gram. Or 1 molecule of CH4 is gonna give you 16 atomic mass unit. So you can see like the inbuilt idea of summation is there. So basically, if you have any object, let's say CX and HY, so I can write this number of carbon atoms X into its mass 12 plus number of hydrogen atoms Y into its mass 1, and that will give the answer for this question. So that's what you can see, like sigma I equals elements, number of elements here, NIMI, where N denotes number of elements and M denotes the atomic mass of carbon or the molecules or hydrogen here in this case. So that's giving you 16. So you see like this is a beautiful application of sigma operator in chemistry. Let's talk about pi operator. As you know, just as sigma denotes summation, we have pi, and which is different from this Greek letter, okay, 3.141, something non-irrational numbers, circle connection, all that. But this capital pi is something different. It is used as an operator. When I call an operator, even plus is an operator. So 2 plus 3 means basically you are adding 2 apples with 3 apples. And this plus, when operates on these 2 baskets, it's basically make a new basket of 5 apples. So in that sense, we tell an operator. So what is pi operator? It's same as sigma. Instead, now every time instead of summation, you are just multiplying it. So pi of xi when I is running from 1 to n is, again we have a box containing xi. Now if I supply x equals 1, this box will reincarnate as x1. Put x equals I equals 2, it will be x2. I equals 3, it will be x3, and so on and so forth. So directly we can multiply all of them, and this is the cool notation of writing this in this beautiful fashion. All the other notation you should recognize from the sigma operator. An easy way to remember is sigma is sum and pi means product. So S for sum and P for product. That's a cool symbol. Again, as usual. Okay. So this is our friend from chemistry where pi operator is being used. Chemistry is making a species that requires 3 steps. So maybe the preparation of a species requires 3 basic steps. So this is your initial product and this is your final product, right? And it's basically composite function of mathematics. So first step will give some output. Again, it has to be processed in the second go and third go and so on. The first step gives 66% yield. So maybe 100 unit you have devoted. So 66% is the effective yield that you are getting. Second step gives 50% of the first output, right? And the third gives 95%. What is the overall percentage that you can harness for this synthesis? So clearly you can see you don't need to know much maths. Basically you can calculate the overall percentage just by pi operator, right? Because overall yield will be yield of the first step into yield percentage of the second step and yield percentage of third step. So let's say if you have 100 unit of something in first step, you are going to gather 66 unit. The second step, it's 50% of 66 unit, right, which is 33. And in third step, it's 95% of 33. So first, let's say 100 unit goes inside. After first processing, you get 66 unit. Thereafter, you get 50% of 66, so 33. And then you get 95%, which is approximately 31.35. So from 100 unit, the final answer is 31.35 is the final yield. So basically what we are doing is we are multiplying all these 3 yield, and that can be simply written in a product fashion. So pi is I equals 1 to 3 yield of step I. Usually, like instead of 3, if it is 30 or 100, then it's better to use the product operator. So the takeaway is very clear. You see how fundamentally we exploit the mathematical tools, or at least mathematical symbols and jargons, to translate chemist language into a mathematical formulation. So this was not that enlightening example. Let's come with the, very often we have to do rounding and significant figures in decimal places. So what is rounding? We round the numbers as follows. Just don't listen to me. You try to, like think of your own. How do you encounter rounding and where exactly you are encountering it? So when you are rounding 467 to the nearest 10, it's basically 470 we often tell. We'll not tell it 460 or 465 because 65 is not the nearest 10 and 60 is a bit more far from 67 because the gap of 7 unit. Hence 470 will be a good approximation of this, right? So there is some sort of rule where you do this. So we can decide the nearest number or a decimal point to round rule. Leave it the same with the next digit less than 5. So if it's less than 5, you can leave it the same because it's more closer to the first number. So we have number is, let's say 13 and we have something 14. So if it is 13.4, it's more closer to 13. Okay, so we don't do anything, and it's 13.6 or 13.7, it's more closer to 14. So that is common sense. Increase it by 1 if the next digit is 5 or more than 5. So now 5 is the tag of what? If it's 13.5, it is like a line of control. You could have rounded it to 13 and 14 both, but usually we give more weightage to the higher things, and there is logic to this. We'll see it later. So second example is 0.314, which is, like not exactly pi, but is following a pi trend. Anyway, to 2 decimal places, how will you round? So you see, like clearly this digit is 4, which is less than 5. So we'll make it 0.31. If it were 0.316 or 0.315, we'll make it approximately 0.32. So this is rounding up to 2 decimal, right? Even 0.317 will write 0.32. And now you know like why it's rounding, because in the actual situation 0.317 and 0.316 might cause a lot of difference, because let's say the amount of like protein in milligram or some deficiency because of some disease, some nutrients. So even one small milligram will have a lot of impact on your system. So it feels misnomer, like how you can write all these 3 as same. So it feels like these 3 are equal. Of course it's no. That's why we are doing roundings. Like approximately we are trying to gauge a feel of that. Next is significant figure. So the name itself is significant, something which is more significant in the process. So here we go. It is used to give an answer to appropriate precision. Okay, we use this significant figure as shorthand for significant figures, and we write a number to a given significant figure. So when we ask to write, let's say up to n significant figure, we only display the first n non-zero digits. For example, rounding up or down. For example, a temperature of let's say 37.678 degrees Celsius to 3 significant figures. So we have just 3 structure you need to take. So before decimal will also be counted, so 37.7, because this guy just after 6 is more than 6. Moreover, 678 is more close to 700 into 600, right? Now for positive decimal less than 1, we start counting the number of significant figure from the first non-zero numbers. For example, 0.009436, 0.0094. It's not 0.00. Can you reason why? Give it a try. We should use significant figure or negative numbers in the same. For example, is minus 137.54 is minus 140. Because you see, if your number is minus 140, a lower number is 141. So clearly this gap is lesser. So we'll make it more biased towards the nearest guy. So I hope you understood this. Let's take an example from chemistry again. We have a reaction of methanol and salicylic acid to form the ester methyl salicylate. So basically, it's benzene ring connected with OH group, and we have double oxygen O connected with OH. And the second thing is methanol is 3OH, and that gives you salicylic acid. Now, of course, water is getting eliminated from the system. So red formation of ester is given by red equals, like the red constant times methanol into salicylic acid. So the concentration of this 2 into red constant. Usually red constant is already given in the question because it is found by the experiment. Concentration of methanol is given 3 mole per decimeter cube, and you have 0.x mole dm minus 3 like per dm cube. Now red, if directly you'll plug the values, you'll get K times concentration of methanol and salicylic acid. That's going to be 7.88706 mole per decimeter cube per second, because it means how fast you are doing, and of course volume also matters. So now our concentration of this is expressed in the fewest decimal. Okay, so 7.88, this if you want to do it in one significant figure, we'll just make it 8 mole per dm cube and per second, right? So this is how you approximate it depending on the situation. Maybe you can do it for some medical purpose, then you have to do up to 2 significant figure or even up to 4 significant figure. Like so, it depends on situations, like up to how much significant figure we want to retain the information. Let's come with a very unusual, and this is one of my favorite applications. It is very fundamental to the mathematical essence. So if you have, let's say, y equal to some mx plus c, we always rearrange it. So like we subtract c from both sides. So y minus c is mx plus c minus c. C minus c is 0 according to the axiomatic definition. And now mx plus c, by additive property of a real numbers with 0, it will remain mx. So now you can divide by m provided m is not 0. And hence this is known as rearrangement. This rearrangement is often used throughout the equations, and one of the favorite example is thermodynamics, where the Gibbs free energy is given by del H minus T del S. So on a very gross sense, a system will always try to minimize its Gibbs free energy, like enthalpy and its entropy under some temperature conditions. So del G equals del H minus T del S is a very, very fantastically important equation in the chemistry. And if you were to find del S, it's nothing but del H minus del G by T. So we are just doing this rearrangement, and it's often useful as a, because most of the time we are more interested in entropy change of the system. From there, heat calculation can be done approximately. Okay, so basically we use this rearrangement equation. So one of the most encountered mathematical tools in chemistry is logarithm. And you can clearly see like it's nothing more than addition or multiplication. So just as addition and multiplication have inverses, which is subtraction and division, we have inverses for the exponentials, and they are called logarithm. So you can see it's just log or something. So this answers the question, how many of one number do we multiply to get other number? So let's say how many of 2 you need to multiply to get 8. So how many copies of 2? It's 3 copies, 2 into 2 into 2. So logarithm is 3. Right, well, so we have a notation and fanciful notation for logarithm. You could have given a star, moon, or whatever as notation. So we have a notation like log, something on its foot and something on its head, and these 2 guys represent something, right? So if you have log log piece of wood, 2 on its feet and 3 on its head. It's better to write, like usually the rituals is to write 3 on the same level as we have log, right? So this represents 2 raised to the power what is 3. So how many times we need to multiply 2 to get 3? And you are like, bro, I'm so frustrated. Because if I ask you log 2 8, it makes sense. 2 multiply 3 times 22 into 2. If I ask 2 1, like 2 to the power what is 1? So 2 to the power 0 is 1. So basically log of half moon star means half moon to the power what equals star, and what is the answer? So if you have, let's say, log 864, 8 to the power what is 64? It's 2. So it's just a language. If I ask log base half 4, half to the power what is 4? Half to the power what is 4? Can you answer? Yes, half to the power what is 4? Okay, if I take 2, it's 1 by 4. Oh, I'm frustrated. So I can write 2 to the power minus 1, 2 to the power 2, base is same. You can equate the powers head because feet is same and you are you. So your head must be same, so hence it should be minus 2. Okay, so log AX is equivalent language. It's just like some Arabic language and you are translating into Sanskrit. So if y equals equal to x, a to the power x, we define x as log AY. And like especially when you define power of hydrogen ion concentration, pH, we are tempted to use minus log H plus. Have you ever wondered what log is doing over here? Since the hydrogen ion concentration for most of the solutions is measured in molarity, so you have 10 to the power minus 8 molar solution or something. So if you write 10 to the power 8 molar like 0.0000000 something, okay, it will be too clumsy to write. So hence we have a decoding of this. Instead we just see like 80 represents 8. So basically what log do is it takes up big numbers, and when you track log to any base, let's say 2 or to 10, then it becomes a smaller version of this. So it's de-escalate, and now it's easy to handle. Like this data handling is easy, and that's the only use of logarithm. So we have got some properties of log. These powers will come, so whatever is on your head will come to your feet. So 5x cubed plus 3x, and then log 10, 10. We call this log to the base 10. Okay, log 10 to the base 10. This base means your foot, and this is head mundi, right? What is log 10 10? It simply means 10 raised to the power what is 10. So it's just a language, right? It's 1. So the answer is 5x cubed plus 3x. Now you can give a try. Why you have, if log, let's say log 10 10 square is there, so 10 to the power what is 10 square is clearly 2. So you can also scam it by taking 2 on its foot. So log 2 10 10. Of course you can prove this from the basic exponential condition, and now we know this is 1 because 10 to the power 1 is 10, so answer is 2. This is enough for our chemistry, right? Of course, one more thing, can you define log 10 minus 1? Okay, let's say it's something Golu. So it's equivalent language as 10 to the power Golu equals minus 1. Now if I take Golu as 0, it will give 1, 10 to the power 1 will give 10, 10 to the power 2 will give 100. So there is no way I can get minus 1 from positive values, right? Even 10 to the power root 3 will give something positive. Whatever minus 1, if I'll take minus 1, 10 to the power minus 1 is 1 by 10, so it's still positive. Oh my god, so this is inconsistent. It means I'll not have any real Golu in the world, maybe some virtual Golu crying. So maybe the answer will be some complex number, or you have to invent something new. Anyway, we are not interested in that. What is of immense consequences is in many equations in chemistry, we need to use only logarithm to different bases. The first one is to base to the power to the base 10, such as pH in the equation, minus log H plus concentration. Usually we like log base to the 10, however we tend to like logs to the base 10 as just log. So example, pH when you see minus log H plus, by default means to the base 10 is there. When you have base something called E, this E is known as natural logarithm. What is E? Okay, so let me give a feel of E first. Let's consider the value 1 plus 1 by 10 to the power 10. What do you feel? It will come. So it's clearly 1.1 to the power 10, and you expect it to be something around 1 point something. What about 1 plus 1 by 100 to the power 100? So do you feel it will increase or decrease? Okay, this thing has decreased, but you are multiplying more times, so maybe it will increase, right? What about 1 plus 1 by 100, 1000 to the power 1000? So again, you see like very close to 1, but you are multiplying many times now. So every time you are getting more and more closer to 1, but you are multiplying more and more copies. So you feel like this product will not grow very fast, okay? And a very challenging step is if you'll see 1 by 10 to the power, let's say 20 to the power 10 to the power 20, you get a very surprising result. It's like 1.000000001 to the power 1000000 times 10 to the power 20, okay? And that's gonna give you 2.7 something something. You are like, what the hell is happening? Okay, this 1.00 is something close to 1. You are multiplying 1000 times, so very small. You know, like added multiple times, multiplication, fundamental addition, that's giving you 2.71. Why not it's giving more than 3 or more than 4? Because this product is not growing rapidly. So basically, if you will take 10 to the power really large, too large, and take the same too large here and you multiply, you'll get the answer as e in the limiting sense. And this is from where that natural logarithm to the base e comes. Okay, you use the notation log base ex as ln x. So if 3 is e to the power x, the other way of telling is x is ln 3. So it's basically log 2.71 something to the base 3. Now 2.71 to the power 1 will be 2.71. So if it is 3, let's execute this for a beautiful chemistry example. We have a general equation which is taking place in the form of some A mole of reactant A and B mole of B is giving you C mole of C and D mole of D, where equilibrium constant is defined as dow dot dow. Okay, so as you know, it's defined at C to the power concentration of product to the power its coefficient and multiplied divided by concentration of reactant, and this is basically C to the power C, D to the power D by A to the power A and concentration of B to the power B. Now you have to find logarithm k as a sum of logarithms. So if we'll take log k on both sides, it's just log of Golu Bholu Bikki Rikki will be log Golu plus log Bolu plus log Bikki plus log Rikki. You can feel like that. Let's say if you have log 4 into 2 to the base 2, so answer is already 3. Now even if you separate log base 4 and log 2, so it's giving 2 plus 1 3, so that matches. Now you might be surprised, it will matches for every time when your product you can convert into sum. Basically what's happening is it's mimicking the idea of exponential. So a to the power x plus y is a to the power x into a to the power y. It's same as this statement. And if you take log, we get nicely log k is minus a log a, minus b log a, c log c and d log c, and it looks more cool. And we have log table and you have to calculate. Log table means like someone else has already done this calculation for you, right? Log 2.713 is 1.09 something something, right? 8 something. So this is already done. How they do? Actually they take 2.71 power 1, that is 2.71, then they'll take power 1.1 and then they'll keep on sandwiching this on the window, and mechanically they used to find this value up to 10 decimal or 20 decimal. Now you are programming where you can insert the values, and using calculus you can get it. Okay, one more way of doing this, basically you can, okay, so sometimes you need to convert logarithm to different base. So how you convert? So let's say if you have log Golu and Bholu, so this can be simply written as log Bholu divided by log Golu. What about the base now? Base is missing, so you are free to select any base. I can select any base of my choice. Let me give you a feel by taking an example. So let's say if you have got log base 2 100 by 10. Okay, so let me give a feel by taking some example. Let's say I gave you log 10 100. So you can simply write it as log of 100 by log of 10. On which base? Your life, your choice. Let's say if I write it on base 10, so log 10 100 by log 10 10, so that will be 2 by 1 2, which is of course 2 here, right? So you might feel like I was fooling you. The beauty is you can even write this as log 2023 base 100 over log 2023 base 10. Now you're like, what does it mean? You see 2023 to the power what will be 100, so that will definitely 0 point something 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 divided by 2023 to the power what is 10, that will be 0 0.0 something else something else something else something else. Now fraction by fraction is definitely that can be true, so it makes sense. Anyway, so this is how you convert it. Log base 10x can be written as log x by log 10. And now usually in chemistry equations we're interested in base e, so by our symbolic representation is ln x ln 10. So this is what is written over. Let's come to a application of this. Okay, so here is a chemistry example. You rearrange the pH of the equation minus log 10 plus and write H plus in terms of this. So if pH is minus log 10 plus, so actually we can take this minus and put on its head minus 1, because from the property log x to the power m on any base is m log same base x, right? So that gives from here 10 to the power pH equal to h plus to the power minus 1. Okay, so 1 by h plus is gonna be 10. Here is another example, and how we can leave trigonometry in right angles. Right angle triangle is always right, in the sense, like, you know, if this is perpendicular, base and hypotenuse, we have a famous Pythagoras theorem, p square plus b square equal to h square. You must have proved it. If you have not, you give it a try, right? So longest side is called hypotenuse, opposite to theta is known as perpendicular, and this is base. So if I'll take this as some angle theta phi, so now this will behave as perpendicular and this is base. It's just nomenclature. And Pythagoras theorem, if you have 3 4, this is going to be root over 3 square plus 4 square, which is 5. Don't tell is plus minus 5. This distance I can clearly see is plus. So we have a structure of solid sodium chloride here. The distance between centers of adjacent chloride and sodium ions is given to 78 picometer. What's the next shortest distance between these ions, right? So basically, what's the length of this red dashed line? And if you see in 3D, so this line and these lines are mutually perpendicular. Why? Because this plane itself is perpendicular to a line. So if we have a plane and a line is perpendicular to the plane, definitely the line will be perpendicular to any line on the plane, right? Because plane is constituted by those lines. So we can clearly see a right angle triangle over here. We can clearly see a right angle triangle. So if I take it out, we have A over here, B over here, and C over here, right? So see the diagram. So this distance is your C, this is D, and this is E, right? So if you consider triangle for the cubilaterals with length ABC, so even these two guys are perpendicular because it's 3D. So ABC are perpendicular. So from here we can find C just by Pythagoras theorem. A and B length, these lengths are same because of the equal ambience of sodium ion. So there is no reason why these bond length will not be same. So C value will get 739 picometer. Now you use the Pytha in this triangle. And you know d square plus c square is going to be e square. So this square, if you add, that will be e square. So once we know from here 393 and the other distance is basically 278 because this is diagonal, right? And this is the side length of this cubic. So that will give you 481 picometer. So I hope you have enjoyed this, the distance, and it's very important in calculation of the bond strength, and that also impacts the crystalline or amorphous structure of a solid. So before I go application with matrix, little bit calculus, let's enjoy. A stationary point we know, like if you have any y as a function of x, what is function? It's like a machine. We have washing machine, you give dirty clothes and you get fresh clothes. So washing machine is a function. Similarly, we can have function like x square, where you give input 1, it will return 1 square. You give 2, it will return 2 square, and so on and so forth. So we know if we graph any function, it's basically input versus output. So this red line shows for a particular input, this side is the output, right? So for f of x equals x square, I'm giving input 1, output is 1, input 2, this side will be 4, at 0 is 0. Okay, so every graph will have that signature having some input and output. At what point you'll get slope dy by dx is derivative 0. So it's a point where the tangent will be parallel, because dy by dx means small change in y with respect to change in x. Okay, in a limiting case when change in x is very small. So like the top point, if we'll just zoom this, it behaves like a straight line, the small segment. So even if the x value is changing, even if you are going from minus 0.00001 to plus 0.00001, the y value still remains same. That's why it is stationed there for a moment, hence is known as a stationary point. Okay, so for this point, like suppose if I take any other point over here, what is the slope? It's positive because the angle it's making is theta. Moreover, as you are increasing in x, as x is increasing, y is increasing, so hence we call increasing nature. So for all these points, slope will be positive. At the peak point, as x is increased, y is not changed, so it's dumb to the insensitive to the increase in x. At this point, x is increasing, x is one-way traffic, it's like time, the y is decreasing, so it's negative, and that's what I've told. So this portion is decreasing portion, because as you increase, you fall. Famous chemistry example to this, and this is John's potential, which it described energy, potential energy between two helium atoms separated by r. So we have two helium atoms which are separated, the center is separated by a distance of r. So the potential energy associated is given by this relation, a by r12 minus b by r6. Is very bizarre to see how this distance and potential is related. So if we graph this, as you can clearly see, when r is infinite, roughly a by infinity is too large minus b by infinity is going to die. It will almost be in ICU, and 0 minus 0 is 0. So at infinity will almost try to touch the x-axis. Definitely will never touch it, because always will be in ICU. When r is too small, like the distance between them is very small, tending to 0, so it will blast. This will also blast, right? But since r to the power 12 will blast more, because 0.00001 to the power 12 something by this will be bigger infinity, right? And b by 0.0001 to the power 6 will be little bit small in tug of war, so this will win. So hence overall the expression at 0 is going to infinite. Okay, but now there is a tug of war. Why? Because as you are moving from infinity to towards, so this term is started, as r increases, this decreases, and this also decreases, but initially this decreases fast, this decreases slow, and later like this will die fast and this will die slow. Okay, so there is a point, of course it will decrease to a limit, and thereafter it will start increasing. So there is a point where you'll get a minimum value of potential energy. And a system will always be in a stable equilibrium, or a system always wants to attain the minimum potential energy. The best practical example you can see, if you are in a standing position, you'll feel more tired. When you are sitting, you are less tired. When you are sleeping, you are less tired. So your potential energy minimum in sleeping, so you are most stable, then stable, and this. There is a spiritual connection to this. If someone is dying or is dissolved in the cosmos, his energy is at the minimum state, and hence the maximum potential energy has attained, so he'll never come back. Anyway, so how to get the radius at which this helium will be in equilibrium position? So for that, just we need to differentiate this function. It means if we differentiate, we want to find a point where the slope will be 0. So this r is special. Now we'll use definitely mathematical tools. So dv by dr, if we'll calculate, x to the power n differentiation is nx n minus 1. So if you have a by r to the power 12, it's a into r to the power minus 12. So it's minus 12 r to the power minus 13, minus 12 minus 1, and times a. Constant will not change, so constant will just be out of the differential operator. So if we'll do all this bunch of calculation, r is 2a by b to the power 1 by 6. So for the equilibrium separation, that magical point was 2a by b 1 by 6. Now this a and b is found from experiment. So basically we know the conditions where stable equilibrium will be attained. So what is matrix? It's defined just as a collection of numbers. So you have a box of numbers which is kept in a good fashion. So we call this as row. So we have first row and second row, and the vertical bar we known as columns. So it's column 1, column 2, and column 3. So every matrix will have some number of rows and some column. So let's say if you have 1 0 0 1, and there is a fanciful notation of putting them. Either you can put on this big bracket, or some authors keep on this small bracket. So we have 2 rows, row 1, row 2, and 2 column here. 2 rows and 2 columns, right? So we use capital letters A and B to denote this matrix. Matrix with equal number of rows and columns is called a square matrix because it feels like they are equal. Okay, so in that sense. So we have 2 rows and 2 columns. So A equals B, so it feels like rectangle matrix becomes a square. Probably that's the name. Okay, so the size of matrix is denoted as like this. You put an index, how many rows are there? 2, and how many columns are 3, and then you multiply. You give 2 cross 3. What does it mean? Because 2 into 3 is 6. So basically we have 6 element, which is clearly wrong. So how many elements are rows? 2. How many columns are there? 2. And we just keep 2 into 2. Don't write 4. I'm giving you the reason. So 2 into 2 means 2 rows and 2 columns. And 2 into 2, 4 means we have 4 objects in the matrix box. 1, 2, 3, 4. So let's see the size of this matrix. So we have 1, 2, 3, 4 into 1, 2, 3. So 4 rows, 3 columns, total 12 elements which you can count. So 11, 12. This one is 3 rows, 1 column. This one 3 rows and 3 columns. Right? Okay, so let's take a chemistry example now. Okay, let's take a chemistry example. Ignoring the hydrogen, find the atom connectivities matrix of butene, but1ene. Okay, so all of you know, like but1ene will give carbon numbering from here 1, 2, 3, 4. So what is atom connectivities? Let's define it. It's a matrix which describes how the carbon in but1ene are bonded with each other. Okay, so what we'll do is we'll level carbon 1 to 4 first. So I've leveled 1, 2, 3, 4. This is 1, 2, 3, 4, right? Okay, fine. What else? Now we are going to use basically a matrix notation. So how will you define the elements of matrix? So we define matrix element AMN as the element present in M row and N column, right? To describe how carbon M and N are bonded, and hence we need to find 4 cross 4 matrix. So you see, A12 means we want how carbon number 1 is bonded with carbon number 2, right? For example, A12 describes how carbon 1 is bonded with carbon 2. What does it mean how carbon 1 is bonded with 2? So we have a double bond between them. So the number of bonds will take. That is how we are defining AMN. AMN is number of bonds within carbon atom at position M and carbon atom at position N. So A12 is going to be 2. What about A23? It's clearly 1. What about A13? 1 and 3 is not bounded at all. So we have 0. There is no bond between them. One exciting thing, what about A11? So carbon atom A1 is definitely bonded with carbon atom 1. So there is no, it doesn't make much sense, like, because you are already bonded with you because you are you. So either you can give a status of 0, it depends on us how we define it, but here is better to give, like it makes sense. Every atom will be bounded to itself, hence we tend to write the atomic number of the atoms for which carbon is 6 over here. So A11 is 1 because for carbon atoms bonded with 1 means everything is bonded with itself. So basically A11 we write it as 6. It's just the atomic number if it is bonded with itself. This is the notation. Okay, now it's of course true for A22. It's bonded with itself, so we'll assign a value of 6. Again A33 is 6 because carbon atomic number. A44 is 6. So now we have a nice matrix because we have 4 carbon atoms. So 1, 2, 3, 4 rows I can create, and 1, 2, 3, 4 columns I can create. And what I'll put over here, A11, it means carbon 1 is bonded with 1, so that will give a status of 6. What about this A12? So carbon 1 and 2, how many bonds are there? 2. A13, 0. A14, 0. A21 is same as A12 because number of bonds with 2 and 1 and 2 is same thing. If I'm friend of you, you are a friend of me, hence we are friend. What about A22? So every atom will be bounded by itself, and by definitions I have chosen it to define as the atomic number of carbon present there. So of course 6. So hence we have a nice matrix here. 62002 6100 161 0016, and this represents what? 1ene. And see how butane is represented in a matrix form. Don't you feel chemistry is cool? Okay, so this was a tribute to chemistry. Very often we see like what is the use of mathematics, and today I wanted to just give you a glimpse of how mathematics formation in a very fundamental way